All right, so we're going to talk about the ratio test and the root test. So these are both series tests where we're going to test for convergence or divergence. And we should spend some time trying to get the main idea behind these tests so that way we can really understand how to use them and when to use them. So the idea is that if a certain series behaves like a geometric series, can we use that to determine convergence? So let's spend some time looking at this series, this geometric series, with 1/3 to the n as our terms. So we know that this is a convergent geometric series because the base is 1/3 and the magnitude of that is less than 1. And now we ask what it looks like when we take the ratio of the terms of 1/3 to the n. So we're taking an plus 1 over an, where an is 1/3 to the n. Let's compute this. So let's look at the an plus 1 part. Okay, we'll take our an down, but we have to substitute the n plus 1 where we had the n. So it's 1/3 to the n plus 1. And now let's look at dividing by an. So we take our an 1/3 to the n, but we have to divide by that, so we take the reciprocal. All right. Now let's take this an plus 1 term and bring it to the numerator of the fraction. All right, so we have 1/3 to the n plus 1 on top, and we're divided by 1/3 to the n. And let's do our exponent rules to the numerator. So let's split up the 1/3 to the n plus 1 as 1/3 to the n times 1/3, and cancel out the 1/3 to the n, and we get 1/3. Okay, so the ratio of the terms is 1/3. This kind of has a better interpretation than the way I just wrote it, but this is how we would just do it algebraically. All right, so here I just wrote out the geometric series. We have 1 plus 1/3 plus 1 over 3 squared, etc. So what does it mean that the ratio of these terms is 1/3? Well, to go from 1 to the next term, 1/3, that means you multiply by 1/3. Then you multiply it by 1/3 again to get to 1 over 3 squared. All right, so that's really our interpretation of what it means to be looking at the ratio between our terms. All right, so just more generally, if we look at the ratio of terms for any geometric series, so our terms in the form r to the n, so for some fixed r, what does that tell us about convergence? So we can do this pretty quickly. The ratio of the terms is always r, just like previously the ratio of the terms was 1/3 when r is 1/3, and we know exactly when this converges. It converges when the absolute value of r is strictly less than 1, and any other time it diverges. So when we look at more complicated series, we want to focus on the ratio of terms and what we can conclude about the series. So here we have a series that is somewhat similar looking to 1 over 3 to the n, except it has n in the numerator. And then what can we say about the ratio of the terms, and what might we think might be true because of the ratio of the terms? Okay, so for your own enjoyment, I wrote out some of the terms of the series. Let's look at the ratio of the terms. So first, let's look at an plus 1. So we'll take our n over 3 to the n, and plug in n plus 1. So we have n plus 1 over 3 to the n plus 1. Now let's look at an. So let's take our an, but we have to divide by it. So take the reciprocal. So I'll flip it around, and it's the same as multiplying by 3 to the n over n. All right, let's simplify this a bit. So we can combine this into one fraction. So this is 3 to the n times n plus 1 on top, and on the bottom, that's just 3 to the n plus 1 times n, but we can split the 3 to the n and the 3. And then the last step is canceling out those 3 to the n's. All right, so this is not as simple as before. We don't just get some simple constant as the ratio. For any n, the ratio would be n plus 1 over 3n. But we can think about what this looks like. So if we take the limit as n goes to infinity, this gets closer and closer to 1/3. So it has this ratio that between the terms, it's like 1/3. So what this tells us intuitively is that it behaves like the geometric series 1/3 to the n. So now we're going to formalize those ideas with the ratio test. So we're going to do exactly what we just did with the last series. We're going to take a limit of the ratio of the terms. I guess I shouldn't say exactly because we can deal with negative terms, in which case we're just taking the absolute value of those things. And we're going to set that limit equal to L. Now, we're not going to go through any formal proof. We just want you to make sure you understand the intuition. And if you do, it's a lot easier to remember the statement of this test. So the idea is that our series behaves like the corresponding geometric series L to the n. And when does that series converge? Well, we know it converges when L is less than 1. So when this limit is less than 1, it turns out that the series we're looking at converges. And not just converges, it also converges absolutely, which is actually we get for free because we're taking absolute values. This geometric series diverges when L is greater than 1. So when our L is greater than 1 or infinity, the series we're looking at diverges. Okay, so where this comparison kind of fails is when L is 1, because the corresponding geometric series does indeed diverge. But at this cutoff point, when our limit is 1, the test becomes inconclusive and there's nothing we can conclude. So that's a bummer, because we can't use the test. So a big giveaway to use this test is when you see a factorial expression. Almost every time we see a factorial expression, we're going to think ratio test. But it can also be useful with certain, but not too complicated, exponential expressions. So we actually did all of the work for this example. The series with n over 3 to the n, we computed the limit of the ratio of the terms. So I'm not going to talk about the work for this because we did this at the beginning of the video. We didn't put the absolute values, but we didn't really have to think about that because these terms are already positive. So when we take the ratio of the absolute values, and then we take the limit as n goes to infinity, we showed that that was 1/3. And so 1/3 is our L, which is less than 1. So what do we conclude using the ratio test? By the ratio test, the series we're looking at converges because L is less than 1.